In this video, we're going to be talking about how to use L'Hopital's rule to evaluate limits that are in an indeterminate form. Now, by an indeterminate form, we mean an expression where even though we can compute what the limit is of the individual pieces, the way they combine together is sort of non-obvious. Now, we've already seen some examples of these limits. For instance, let's take the limit as x goes to infinity of x squared plus 3x divided by 2x squared minus 4. Now, what makes this an indeterminate form, technically, even though we know how to solve it, is that this is a fraction, and the functions on the top and the bottom of the fraction are both going to infinity. They're both getting very, very large. If I look at this numerator and think about what happens as x goes to infinity, as x gets very, very large, well, when x gets very large, then x squared gets very large, and so does 3x. And so this whole expression goes off towards infinity. This denominator does the same thing. As x gets very, very large, 2x squared gets even larger. Minus 4 doesn't change that. And so this denominator also goes off towards infinity. And this is going to be a type of expression, a type of limit that we're going to say has an infinity over infinity indeterminate form. Now, it's called indeterminate because I could come up with lots of different examples of a limit with something on the top going to infinity and something on the bottom going to infinity, but where the actual limit, the actual value of it, could be lots of different things. This limit could be 0, it could be infinity, it could be some number in between. And because of that, when the numerator and the denominator are both going to infinity, we don't know immediately what the answer is going to be, what the limit is going to be. Now, as I said, we know how to solve this. We know a way of solving this problem. We can multiply the top and bottom of this fraction by 1 over x squared and say that this is the same as the limit as x goes to infinity of 1 plus 3 over x divided by 2 minus 4 over x squared. And now 3 over x goes to 0 and 4 over x squared goes to 0 as x goes to infinity. That means that this limit becomes 1 plus 0 over 2 minus 0, which is just 1/2. And great. When we have an indeterminate form that just involves polynomials or polynomials and radicals and roots, we can always use algebra in order to determine what the value of the limit is. However, there are lots of situations where that's not the case, where we're not just looking at polynomials over polynomials. Let me take another example. Let's look at the limit as x goes to infinity of x squared divided by the natural logarithm of x. Now, just like before, the numerator of this fraction is going off towards infinity. Now, the denominator of this fraction is natural logarithm of x. If I come over here to the side and I remember what the natural logarithm of x looks like, I know that the graph of natural logarithm of x looks something like this, which tells me that as x goes to infinity, natural logarithm of x also goes to infinity. As we move further and further to the right on the natural logarithm graph, the y values keep getting bigger and bigger. So that means that this denominator is going towards infinity. So this is another example of an indeterminate form. This is again an infinity over infinity indeterminate form. The problem that we're going to solve today is that we can't just use algebra in order to evaluate this limit the way that we could the previous example. And that's basically because x squared is a polynomial function and natural logarithm of x is a logarithm function. And they're basically just two different kinds of functions. Algebraically, they're not going to have any sorts of interactions or identities between each other that we're going to be able to take advantage of. Now, there are lots of arguments that can be made here for what this limit is. If you look at the graphs of x squared and natural logarithm of x and compare them, you could say that, well, the graph of y equals x squared, that looks like a parabola, and so that function looks like it's growing much faster than the graph of natural logarithm. So it looks like the numerator of this fraction is growing faster than the denominator. So maybe that means the limit is going to be infinity. And while that's good intuition, it's not a proof. And so what we're going to be looking at today is a tool that we can use to actually evaluate this indeterminate form, and it's called L'Hopital's rule. Let me go ahead and write that down. So, theorem. This is L'Hopital's rule. It says that if the limit as x approaches a of f of x over g of x is an infinity over infinity or a 0 over 0 indeterminate form. Excuse me. Then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x, when we can evaluate this new limit. So notice that what we've done here, or what L'Hopital's rule says that we can do, is when we have an indeterminate form, an infinity over infinity, or a 0 over 0 indeterminate form, we can take the derivative of the numerator and the denominator separately. This is not using the quotient rule. This is taking the derivative of the numerator and the derivative of the denominator separately and evaluate that limit. And if we are actually able to evaluate that, then that will give us the same limit as the original limit we were looking for. So let's see how that looks up here in the previous example. We have the limit as x goes to infinity of x squared over natural logarithm of x. We check to make sure that this is an infinity over infinity indeterminate form, because that's the only situation, infinity over infinity indeterminate form or 0 over 0 indeterminate form, that we can apply L'Hopital's rule in. We do have that. This is a valid place where we can apply L'Hopital's rule. And so, according to L'Hopital's rule, this limit is the same as limit as x goes to infinity of, and now we're going to take the derivative of the numerator and the derivative of the denominator separately. Now, working that out, we know the derivative of x squared is 2x, and we know the derivative of the natural logarithm of x is 1 over x. And now we have a new limit, but notice that unlike before where we had one polynomial and one logarithm, two very different kinds of functions, we now have an expression that involves a bunch of x's and some fractions, which is just fine. If we go ahead and finish this off, we can simplify this right-hand side by flipping and multiplying that denominator. So 2x over 1 over x is the same as 2x times x over 1, which gives us the limit as x goes to infinity of 2x squared. Apologies. Let me move this down here where it's visible. So we get the limit as x goes to infinity of 2x squared, which is infinity. So we were able to conclude, using L'Hopital's rule, that this limit of x squared over natural logarithm of x really is infinity. Now, let me be a tiny bit more precise about when we refer to one of these limits as an infinity over infinity or a 0 over 0 indeterminate form. Then we'll do some more examples, and then we'll talk about some other indeterminate forms that we can still use L'Hopital's rule on. So we say that the limit as x goes to infinity of f of x over g of x has an infinity over infinity indeterminate form if the limit as x goes to a of f of x is equal to plus or minus infinity, and the limit as x goes to a of g of x equals plus or minus infinity. Also, we say that the limit as x goes to a of f of x over g of x has a 0 over 0 indeterminate form if the limit as x approaches a of f of x equals 0, and the limit as x approaches a of g of x is equal to 0. So these are the situations in which we may apply L'Hopital's rule, when we have the limit of a fraction and the top and bottom either both go to an infinity, they could be positive or negative, or the top and bottom both go to 0. Those are the places where we can't work out instantly what the limit's going to be and where L'Hopital's rule can apply. All right, let's do another example. Let's suppose we have the limit as limit as theta goes to 0 of sine of x over x. This is actually a classic limit, which I should be writing using thetas, of course. The limit is theta goes to 0 of sine of theta over theta. Now, in this case, x is not, our input theta is not going to infinity, it's going to 0. And so we can look at the numerator and denominator separately. Let me do that explicitly. If I look at just the numerator over here of this example, I have the limit as theta goes to 0 of sine of theta. We know that sine is a continuous function, which means that if I want to take the limit of sine at a particular number, I just need to plug that number in. So the limit as theta goes to 0 of sine of theta is sine of 0, which is 0. And then, of course, the limit as theta goes to 0 of theta, well, that's, of course, just 0 as well. So that means that this numerator is going to 0, this denominator is going to 0, which means that we do indeed have a 0 over 0 indeterminate form, and so L'Hopital's rule can apply. Now, L'Hopital's rule says that I can, in this case, replace the numerator and denominator with their derivatives. Let's go ahead and do that. We know that the derivative of sine theta is cosine theta, and the derivative of theta is just 1. Now, one thing that I do like to do when applying L'Hopital's rule is to give an indication that I've done this, because when you apply L'Hopital's rule, the fraction that you are taking the limit of can change the way that it looks quite a lot. It's not always easy to see if you go back and read it again how you got from one place to another. So I like to give a little indication that I've used L'Hopital's rule, and I do that just by putting an L apostrophe H here above the equal sign, which tells me that L'Hopital's rule is what I use to get from the left side of the equal sign to the right side of the equal sign. That's not a necessary mathematical component, it's just a very good reminder so that when you go back to review it or if someone else reads your work, they can know what you did. All right, so now we're at a point where we've got the limit as theta goes to 0 of cosine of theta over 1. Now, we can take the limit of this expression because now everything in sight is continuous and there are no more zeros in denominators. So we can write this as simply cosine of 0 over 1. We know that cosine of 0 is 1, and so 1 over 1 just gives us 1. So that tells us that the original limit as theta goes to 0 of sine theta over theta is equal to 1. There are other kinds of indeterminate forms that we can run into, not just infinity over infinity or 0 over 0. We can often use L'Hopital's rule to evaluate those. But let's talk about some of those other indeterminate forms. We have indeterminate forms like 0 times infinity. If I've got something that's going towards 0 times something that's going towards infinity, it's not always clear how those two are going to balance out, which one is going to win. We also have things like 1 raised to the infinitieth. That is uh, that is indeterminate because 1 raised to anything should be 1, but if I take something that's anything that's even a little bit different from 1 and raise it to a number that's getting larger and larger and larger, that's either going to go off towards infinity or down towards 0. Similarly, 0 to the 0th is an indeterminate form. 0 to the 0th is not defined. And so knowing what a 0 to the 0 indeterminate form is unclear. And we also have things like infinity minus infinity, where if I've got two things that are going to infinity and then I subtract them, it's very much unclear which one of those is going to win. Am I going to get infinity, negative infinity, 0? All these things are unknown because, of course, infinity is not a number and so it doesn't follow the same rules as regular numbers. So we're going to talk about how to handle some of these indeterminate forms. Now, this first one here, this is the simplest one because any product can always be rewritten into a quotient, into a fraction. So to handle a 0 times infinity indeterminate form, we're going to rewrite as a complex fraction I should say sometimes it's a complex fraction. We just want to write it as a fraction. That's going to be in a 0 over 0 or infinity over infinity indeterminate form. Let's look at an example. Suppose I want to take the limit as z goes to infinity of z squared times to the e to the negative z. So I can see that I'm taking the limit of a product, z squared times e to the negative z, and I can look at what each one of these things does. Now, as z goes to infinity, z squared is going to go to infinity, of course. Now, What about e to the negative z? If I think again uh, about the graph of e to the z, I get z here, then the graph of y equals e to the z looks like this. So if z was going off to infinity, then we would get, then this would limit would be infinity. Then e to the z would be going to infinity. But we are looking for e to the negative z. So as z is going to infinity, negative z is going to negative infinity. And from over here in our side work, we can see that the limit as z goes to negative infinity of e to the z is 0. So if that input to the exponential is 0, is going to infinity, then the outputs e to the z are going to 0. So that means that this e to the z piece is going to 0. So my expression z squared times e to the negative z has two pieces. One of them is trying to make the whole expression get bigger, z squared. It's going to infinity, wants to make the whole expression get bigger. E to the negative z, though, is going towards 0, and it's trying to bring everything smaller, trying to make the whole expression be small, closer and closer to 0. So they're fighting against one another, and this is an indeterminate form. Now, we would like to apply L'Hopital's rule, but L'Hopital's rule only applies to 0 over 0 or infinity over infinity indeterminate forms. And so what we would like to do is we would like to rewrite z squared times e to the negative z as a fraction. Now, there are always going to be at least two ways of doing this. So let's consider those two ways. I have z squared times e to the negative z. One way that you can do it is you can take part of the expression, z squared, and put it in the denominator, or rather put its reciprocal in the denominator. So notice that z squared times e to the negative z is the same thing as e to the negative z divided by 1 over z squared. So e to the negative z over 1 over z squared, or we could write that as e to the negative z over z to the negative 2 is a way of writing this expression. And now notice that e to the negative z is still going to 0 like we had before, but z to the negative 2 is now also going to 0 because as z goes to infinity, z squared goes to infinity, and so 1 over z squared is going to 0. So this is one possibility, and the other possibility is to move the exponential piece into the denominator. So I could instead write this as z squared over 1 over e to the negative z, which is the same thing as z squared over e to the z. Now this is an infinity over infinity indeterminate form. So we have two different ways of writing our function that are in indeterminate forms, which L'Hopital's rule would apply to. It takes some experience to know which of these is more likely to be useful. However, one thing that we can note is that if we're going to apply L'Hopital's rule, then in both cases, we would wind up taking the derivative of a power of z, either the derivative of z squared in the right-hand possibility, or the derivative of z to the negative 2 for the left possibility. We know that when we take the derivative of polynomials, their degree drops by 1. So if I take the derivative of z squared, I'm going to wind up with an expression involving z to the first. And if I take the derivative of z to the negative 2, I'm going to wind up with something involving z to the negative 3. Generally speaking, you want to do those things. You want to make the choices which is going to make your next step of the computation simpler. And generally speaking, I would consider powers that are smaller in absolute value, closer to zero, to be simpler. So, thinking through what the next couple of steps would be here, I think I would rather use this right-hand side. I think I'd rather use this right-hand side because when I take the derivative of z squared, I get something involving z, which is simpler. But if I take the derivative of z to the negative 2, I get something involving z to the negative 3, which is more complicated intuitively. So we're going to use this one. Give myself some more space. So, going back uh, to the original problem, we have the limit as z goes to infinity of z squared times e to the negative z, which is the same thing as the limit as z goes to infinity of z squared over e to the z. Now, this is an infinity over infinity indeterminate form, like we just said, which means that we may use L'Hopital's rule to take the limit as z goes to infinity of, and now we'll take the derivative of the numerator and denominator. The derivative of z squared is 2z, and the derivative of e to the z is e to the z. So now, L'Hopital's rule says that if the limit on the right exists, then equals the limit, the original limit we started with. So, looking at what we've got, we have the limit as z goes to infinity of a fraction again. Let's think about what's happening here. Now, as z goes to infinity, of course, e to the z goes to infinity, and 2z also goes to infinity, which means that we wound up with another infinity over infinity indeterminate form. Well, the great thing about L'Hopital's rule is that it doesn't have a limit to how many times you can apply it. We can apply L'Hopital's rule again whenever you have an infinity over infinity or 0 over 0 indeterminate form. Which means that we can take the derivative of the numerator again and get that 2z becomes 2 when you take the derivative, and take the derivative of the denominator again. The derivative of e to the z is e to the z, and get this expression. Now, this is no longer an indeterminate form, because while the denominator is still going to infinity, the numerator is now just a constant 2. This is not an indeterminate form. If we were to describe the form of this expression in the same sort of way that we were doing before, then we would say that this is a 2 over infinity form, but that is not indeterminate. We know that if we take a constant and divide it by something that's getting larger and larger and larger and larger, well, in that limit, we're taking a constant divided by something that's getting huge. And a constant divided by a very, very large number goes to 0. So that tells us that the limit we started with, z squared times e to the negative z, does in fact give us 0. So this example demonstrates two things. It demonstrates how to handle a 0 times infinity indeterminate form by rewriting it as a 0 over 0 or infinity over infinity, and also illustrates a situation in which we might have to apply L'Hopital's rule repeatedly in order to get to an answer. Now, notice that if we had chosen instead to use the left rewriting of the function, then no matter how many times we applied L'Hopital's rule, we would never get out of the indeterminate form. We'd actually be stuck in 0 over 0 indeterminate form over and over and over forever. So it actually made quite a big difference that we use the correct form over here. Now let's look at how to handle some of the other indeterminate forms. One of the indeterminate forms that comes up is an exponential one. So there are several types of indeterminate exponential forms. So we mentioned 1 to the infinitieth, 0 to the 0th. Infinity to the 0th is also one like this, where it's unclear if I've got a base that's going to one of these bases and an exponent that's going to one of these exponents. It's unclear what the answer is going to be. So our general strategy here is going to be to use logarithms, usually the natural logarithms, to rewrite the expression um, as a product or and then as a fraction. So let's take an example here. Suppose I want to find the limit as x goes to 0 of cosine of x raised to the 1 over x. So we can see about what's happening here. Sorry, that should be the limit as x goes to 0 from the right. So let's see what's happening here. So I know that as x goes to 0, cosine of x goes to cosine of 0, which is 1. The inside of this fraction is getting closer and closer to 1. However, the exponent here is getting closer and closer to positive infinity because as x goes to 0 from the right, 1 over x goes to positive infinity. And so what happens is that as x gets closer to 1, as x gets closer to 0 from the right, we have that cosine of x is a little less than 1. So when x is a tiny positive number, cosine will be a number just a tiny bit less than 1. And 1 over x is a large positive number. Now, usually, if I take a small number, less than 1, and raise it to a large number, that should go to, uh, that should be small. And so the fact that we're taking something that's less than 1 and raising it to a very, very high power suggests that, that should be going off towards 0. That should be getting to be a very small number. But on the other hand, 1 raised to some large number should be 1. And so we know that cosine of x isn't actually going to be equal to 1, but it's going to be really, really, really close. And so the base and the exponent are again fighting against each other. The base of the exponential, which is going towards 1, tries to make the whole expression equal to 1. The exponent, which is going off towards infinity, is trying to make the whole expression equal 0 because we're taking something less than 1, raising it to that power. So these two things are fighting against one another, and we want to work it out. So the way that we will typically do this is we will, as said, use logarithms to do this. In my opinion, the easiest way here is to introduce a new symbol to stand for the limit that we're trying to compute in the first place, and then manipulate that. So what I'm going to do is I'm going to introduce a new symbol, capital L, and I'm going to let L be the limit as x goes to 0 from the right of cosine of x raised to the 1 over x. Now, because I've got this expression, I can take the logarithm of both sides. And so this tells me that the natural logarithm of L is equal to the natural logarithm of the limit as x goes to 0 from the right of cosine of x to the 1 over x. Now I'm going to use the fact that the natural logarithm is continuous. And what that means is that a limit that's inside a logarithm can be pulled out to the outside. A continuous function has this property. So that means that I can write this as the limit as x goes to infinity of the natural logarithm of cosine of x raised to the 1 over x. The reason why we do this is because of the properties of logarithms. The one that we're going to take advantage of here is the fact that for a logarithm, if I have a logarithm of an exponential expression, base raised to power, that power can be pulled out in front. So we get the limit as x goes to 0 of 1 over x times the natural logarithm of cosine of x. Now, once you're at this point, you are going to be in you're going to be in a 0 times infinity indeterminate form. Notice that as x goes to 0 from the right, 1 over x goes to infinity. But as x goes to 0 from the right, we know cosine of x goes to 1, but natural logarithm of 1 is 0. So we are back into an infinity times 0 indeterminate form. That means that we're going to follow the same sort of strategy that we did in the previous example, and we're going to rewrite this as a fraction. Now in this case, we can do that easily because we've got this 1 over x factor at the beginning, and we can just rewrite this expression as the natural logarithm of cosine of x all over x. And now this is a 0 over 0 indeterminate form. Therefore, we can take L'Hopital's rule and apply it here to get that this is the limit as x goes to 0 from the right of, and now we need to take the derivative of the top and bottom here. The bottom is, of course, easy. The derivative of x is just 1. The numerator here, this we're going to have to use the chain rule on, so it's not a bad idea to just do some side work to see what we need here. If I take the natural logarithm of cosine of x and I want to take its derivative, well, I know that the derivative of natural logarithm of something is 1 over that thing. And then I know I need to multiply by the derivative of the inside, cosine. And the derivative of cosine is negative sine. And so that's the derivative of natural logarithm of cosine of x, my numerator. And so that means that I'll have 1 over cosine of x times negative sine x in my numerator here. Let me rewrite this a little bit simpler. Of course, we don't need the over 1 here, so I can just write this as 1 over cosine of x times negative sine of x. Now, you could, of course, write this. This can be written as like negative tangent of x, but in this case, we don't need to. We're actually now in a situation where we can just take the limit by plugging in 0. Every time you rewrite one of these limits or apply L'Hopital's rule or do anything like that, you just take a second to say, all right, am I in a place where I can just plug in the limit now? And in this case, we can, because if I try plugging in 0, I'll get cosine of 0 in the denominator here, but cosine of 0 is just 1, that's fine. And then sine of 0 is 0, but that's not a problem because that's not in a denominator or anything. So this becomes 1 over cosine of 0 times negative sine of 0. Cosine of 0 is just 1. Sine of 0 is 0, which means we get 1 over 1 times negative 0, which all works out to be 0. Now, a big warning here. It's very tempting at this point to stop, but we're not done. Remember that our goal originally was to find this limit, the limit as x goes to 0 from the right of cosine of x raised to the 1 over x. We got through all of this and we wound up with this limit only after declaring that L is this limit that we're trying to find out. And what we worked out here is the natural logarithm of L. So what we have concluded is that the natural logarithm of L is equal to 0. L's what we're looking for, though. So since the natural logarithm of L is 0, I can exponentiate both sides to say that this means that e to the natural logarithm of L is equal to e to the 0th. Now, e and the natural logarithm, they cancel each other out. They're inverses of each other. And then e to the 0th is 1. So that is the limit that we're looking for. And so we can write down as our final answer that the limit as x approaches 0 from the right of cosine of x raised to the 1 over x equals 1. Now, this strategy works for not only the 1 to the infinitieth indeterminate form that we did here, but this same idea works for all of the indeterminate exponential forms. 0 to the 0th, infinity to the 0th. You can apply a logarithm to turn this into turn this expression into a 0 times infinity indeterminate form, which then can always become a 0 over 0 or infinity over infinity indeterminate form, and L'Hopital's rule again comes to the rescue. Finally, let's look at an example of an infinity minus infinity indeterminate form. Let's find the limit as x goes to infinity of 3x minus the natural logarithm of 10x plus 2. Now, looking at each of these pieces, as x goes to infinity, 3x goes to infinity. We've already seen that as x goes to infinity, the natural logarithm of x goes to infinity. And of course, if x goes to infinity, 10x plus 2 goes to infinity, and so the natural logarithm of 10x plus 2 goes to infinity. So this is an infinity minus infinity indeterminate form, where the two sides are, again, competing against one another. One is getting larger, or they're both getting larger, rather, but one is being added and one is being subtracted in here, and so this can come out lots of different ways depending on the exact form of the functions involved. So for this one, our strategy is going to be kind of the inverse of what we did on the previous one. Is we're going to use exponentials to rewrite the limit we want. Again, what I want to do is I want to let L be a new variable to stand for the limit that we want. So L will be the limit as x goes to infinity of 3x minus the natural logarithm of 10x plus 2. Then we have that we can exponentiate both sides. So that means that e to the L will be e to the limit as x goes to infinity of 3x minus the natural logarithm of 10x plus 2. The exponential function, just like the logarithm function, is continuous, which means we can pull this limit out in front and write this as e to the 3x minus the natural logarithm of 10x plus 2. Now, the reason why we're doing this is because we want to change this subtraction, infinity minus infinity, into a fraction so that we can use L'Hopital's rule. It all comes back to using L'Hopital's rule. And so here we're going to use the fact that when I have an exponential raised to a difference, e to something minus something, I can rewrite that as e to the e to the first thing divided by e to the second thing. So this is one of our rules of exponents, and we're taking advantage here of the fact that an exponential turns a difference of things into a quotient of things. Now, here we are in good shape because we can simplify things a little bit here. In the numerator, we can leave it as e to the 3x. But in the denominator, notice that we have an e to the natural logarithm. Just like at the end of the previous problem, e and natural logarithm cancel each other. So e to the ln of something just gives back that thing. So that denominator becomes just 10x plus 2. We are now back in a situation very similar to the first couple we looked at, where we've got an infinity over infinity, indeterminate form. I'm going to rewrite that down here. And therefore, we can apply L'Hopital's rule. Now, L'Hopital's rule says that we're going to take the derivative of the numerator and the derivative of the denominator. Well, in the numerator here, we've got e to the 3x times 3, because 3 is the derivative of 3x inside the exponential. And the derivative of 10x plus 2 is just 10. So now we have a limit. The numerator is going off towards infinity still, because as x goes to infinity, e to the 3x goes to infinity. And the denominator is just going to 10. It's just a constant. And so we have a numerator which is getting larger and larger and larger, a denominator which is staying the same, which means that the value of this whole limit is going to be infinity. So now we have that e to the L is going to infinity, and so L, which is the natural logarithm of e to the L, is also going to be infinity. And that's because since e to the L here is going to infinity, and again, once again, the natural logarithm of something going to infinity goes to infinity, that means that the original limit was infinity as well. So this tells us that as our final answer, our limit as x goes to infinity of 3x minus the natural logarithm of 10x plus 2 equals infinity. Now, here at the end, I did want to give a slightly alternate handling of the exponential and infinity minus infinity forms. Sometimes introducing the L variable, like we did here, can be very helpful. Occasionally, it's a bit confusing, and some of that's down to personal preference. So I did want to very quickly talk about how you can go through the two problems that we did with the exponential and infinity minus infinity form without introducing any new variables, because it absolutely can be done. So let's take, for instance, our expression, the limit as x goes to 0 for the right of cosine of x to the 1 over x. The idea is still that we want to use a logarithm in order to make this work, in order to turn this exponential into a fraction. Rather than introducing something new, what we can do is we can take advantage of the fact that the exponential and the logarithm are inverses of each other, which means that at basically any time, as long as the number that you're looking at is positive, you can write this expression as e raised to the natural logarithm of cosine of x to the 1 over x. And that's just because of the fact that any number a that's positive, a is equal to e to the natural logarithm of a. So that's just something you can always do. If you've got a positive number, is you can replace the a with e to the natural logarithm of a. And from here, the next couple of steps look very much the same, where we have the limit as x approaches 0 from the right of e to the natural logarithm, 1 over x times the natural logarithm of cosine of x, which is the limit as x goes to 0 from the right of e to the natural logarithm of cosine of x divided by x. Now, at this point, we know that the exponential function is continuous, and so if we can work out what this limit is here, what this exponential, what this exponent is, then we can handle things and finish the computation. So if we do some side work, limit as x goes to 0 from the right of natural logarithm of cosine x divided by x, then L'Hopital's rule tells us that this is the limit as x goes to 0 from the right of 1 over cosine of x times negative sine x, all divided by 1, just like we had before. Which gives us the limit as x goes to 0 from the right of 1 over cosine of 0, which is 1, times negative sine of 0, which is 0, which all works out to be 0. So because our the limit of our exponent is 0, that means that the limit of e to that exponent is e to the 0th, which is just 1. So that's an alternative way of doing that first example. Similarly, if we wanted to take the limit as x goes to infinity of 3x minus the natural logarithm of 10x plus 2, we could do the same sort of thing. Now, in this case, we know that we want to take e raised to this because we want to turn this difference into a fraction. So we can do the same sort of thing where instead of doing e to the natural logarithm of the expression, we can switch the order and write this as the natural logarithm of e raised to the 3x minus the natural logarithm of 10x plus 2, which is the limit as x goes to infinity of the natural logarithm of e to the 3x over e to the natural logarithm 10x plus 2 using rules of exponents, which is the limit as x goes to infinity of the natural logarithm of e to the 3x over 10x plus 2 using the fact that the exponential and the logarithm cancel each other out. Now, here, once again, we can do some side work using the fact that the logarithm is continuous. So the side work is that the limit as x goes to infinity of e to the 3x over 10x plus 2, that's equal to, by L'Hopital's rule, the limit as x goes to infinity of 3e to the 3x divided by 10, which we know is infinity. So that means that up here in this limit, the inside of the logarithm is going off towards infinity, which means that the limit of this whole expression is infinity. And that's because the natural logarithm grows to infinity as its input grows to infinity. And so this allows us to see the limit existing just by a string of equalities. We do some side work, but the main line of reasoning just starts with the limit that we're trying to work out equals, and then gets us to infinity at the end. So Both methods can work. It's mostly a matter of style, which way you like to set these things up. And that's all we're going to talk about for today on the uh, great power and very convenient theorem that is L'Hopital's rule.